Section 23.2. The simplest one-electron molecule, H2 plus, H2 with one positive charge. An H2 plus molecule consists of three particles, one electron and two nuclei. The Schrödinger equation of this molecule is this. The kinetic energy operator for the electron, the attraction between this electron and nucleus A, the attraction between this electron and nucleus B, the repulsion between nuclei A and B. And this is the total energy operator minus the kinetic energy operators for the two nuclei. And again, we will be able to calculate the kinetic energy of the nuclei separately. So now, when we apply this Hamiltonian to H, we should get E8 to psi. We should get E psi. And E is the total energy of this molecule. So I want to show you the diagram of this molecule. Nucleus A, nucleus B, the electron. You have one proton here, another proton, and then a negatively charged electron. The distance between the electron and nucleus A is r sub A. This is r sub B. The distance between the two nuclei is the uppercase R, or the uppercase R sub AB. Just to specify that this distance is the distance between nucleus A and nucleus B. Let's look at the potential energy of this H2 plus molecule before and after the bond formation. So the potential energy felt by the electron is the most negative when the electron is close to the nucleus. So that's why you see very negative sign here, very negative sign here. All right? And when this H2 plus molecule forms a bond, and when the two nuclei are at the equilibrium position, so this R sub E is the equilibrium distance, and then you'll see the potential energy curve changes a little bit. Okay, it's negative here versus close to zero here, right? And now let's look at the wave function. So if you have the electron close to nucleus A, and this is the wave function of a neutral hydrogen atom. Over here, this is H plus. There's no electron here. Now, what if nucleus A and nucleus B are at this equilibrium distance? Now let's look at this wave function. This wave function now is symmetric with respect to the center between the two nuclei. So you have a maximum here close to A and another maximum close to B. In the middle, you have a significant overlap. And this is the so-called bonding. You have one bonding electron being shared between A and B. The molecular orbital for the H2 plus molecule can be approximated by the linear combination of the two atomic orbitals. So this is the 1s orbital centered on A, 1s orbital centered on B. C sub A and C sub B are the molecular orbital coefficients. They are just numbers, usually real numbers. In the above equations, so this equation, this phi of H1SA is e to the power of negative RA. So this is simply the exact wave function of the hydrogen atom A. And this wave function, e to the power of negative RB, is the exact wave function for the hydrogen B. Ra and Rb are the distances between this electron, there's only one electron, and the nucleus A and the nucleus B respectively. So over here, when you look at this, you should imagine the nucleus A and the electron form a hydrogen atom, and we can solve the Schrodinger equation for that hydrogen atom exactly. And this is the exact wave function. All right? And the nucleus B is simply a proton. Now here, you need to imagine now nucleus B and the electron together form a hydrogen atom. And we can solve the equation. We get the exact wave function, which is e to the power of negative Rb. All right? Nucleus A, this time, is just a proton. Now, we can express Ra and Rb in this forms. Again, Ra and Rb are simply the distance between the electron and the nucleus. So this lowercase x, y, and z are the Cartesian coordinates of the electron. The uppercase xa, ya, za are the Cartesian coordinates of the nucleus A. The uppercase xb, yb, zb are the Cartesian coordinates of nucleus B. So again, we're using this LCAO-MO theory. So the molecular orbital is constructed by forming the linear combination of two atomic orbitals. In this case, one is A and one is B of the two hydrogen nuclei. Ca and Cb are the molecular orbital coefficients. So again, this is a linear combination of the atomic orbitals. This H2 plus molecule has a very high symmetry, D infinite H symmetry. It belongs to this D infinite H point group. And therefore, we know this Ca squared must be equal to Cb squared. We should have the same weight from nucleus A and from nucleus B in the molecular orbitals. By solving this equation, we get Ca is equal to plus minus Cb. When Ca is equal to Cb, they have the same sign. We say the two 1s atomic orbitals are in phase. They form a bonding MO via the constructive interference of these two AOs. This MO is symmetric with respect to the center of this molecule. And we use G or Gerarder to specify the symmetric property. So we say this is a sigma G bonding orbital in the H2 plus molecule. Ca can also be negative Cb. In this case, the two 1s atomic orbitals are out of phase. The formed molecular orbital is destructive interference of the two AOs. This MO is anti-symmetric with respect to the center of this H2 plus molecule. We say this MO has the Ungerade or U symmetry. And this is denoted by sigma U star, anti-bonding orbital. So again, sigma, that's the symmetry of the bond. G and U are referring to symmetric or anti-symmetric with respect to the center of the molecule. When you see a star here, it means anti-bonding. So again, when you have this asterisk in the superscript, here it means anti-bonding. But sometimes when we look at, for example, quantum mechanical postulate 4, this asterisk in superscript is referring to the complex conjugate of the wave function. So again, unfortunately, we have the same symbol that denotes two completely different meanings. Now I want you to look at the shape of the sigma G bonding orbital and this sigma U star anti-bonding orbital. This bonding orbital has lower energy than the 1s orbitals. This anti-bonding orbital has higher energy than the 1s atomic orbitals. Over here, you don't see any node. Over here, you see a node between these two nuclei. This planar node is right in the middle. We can normalize this molecular orbitals. How do we normalize a function? We simply need to set the integral of the squared modulus of the wave function to 1. And then we can solve this equation. Psi sub g, again, is Cg times the wave function of 1sa plus the wave function of 1sb. So we have this 1sa squared, 1sb squared, and 2 times 1sa times 1sb as the cross terms. And then we have this equation. I think it's better to slightly format this better. This is not really formatted well. I need to put this term, so this term in the square bracket. So insert equation, square bracket, right here. Now this is good. To simplify this equation, we define the overlap integral as sub AB as the integral of the product of 1sa and 1sb. So the integral of this is defined to be SAB, and then we can plug it in. So you're looking at 2 times SAB here. This is 2 times SAB, and then we have the expression for C sub G. And again, G means gerade, or even, or symmetric. So this is C sub G. Therefore, the normalized wave function for the bonding MO is this. What about the antibonding, sigma U? Well, similarly, we have this expression. You just need to replace this negative sign with plus sign with a negative sign. Plus sign with a negative sign.